My name is Professor Andrew Nix from the University of Bristol in the United Kingdom. I'd like to run you through my presentation entitled Next Generation Wi-Fi, Future Devices and Challenges. This presentation was originally given at the Mobile World Congress in Barcelona in February 2014. It was given as part of the Multimedia Content Delivery onto Mobile Platforms session. I received my BEng and PhD degrees from the University of Bristol in 1989 and 1993 respectively. I'm currently Professor of Wireless Communication Systems at Bristol. I also head up the Electrical Electronic Engineering Department and also the Communication Systems and Networks Group. My main research interests cover antennas, propagation, cellular network optimization, and advanced digital modulation and reception. Of particular relevance to this presentation, I was a founder member of the ETSI Res 10 committee, which from 1992 to 95 developed Europe's first wireless LAN standard. This slide summarizes the evolving data rates for the Wi-Fi standards. The original standard offered 2 megabits per second. This was upgraded to 11 megabits per second with 11B, and with the introduction of 11AG and OFDM technology, peak rates rose to 54 megabits per second. 802.11n introduced MIMO signal processing and offered rates of between 3 and 600 megabits per second depending on the number of spatial streams supported. The latest release, 802.11ac, now offers 1.3 gigabits per second at the physical layer, and this translates to maybe 700 to 800 megabits per second at the application layer for a single user operating in an interference-free environment. As you can see, these particular rates are taken from the link shown on the slide. One of the areas where there's quite a lot of confusion in Wi-Fi is the way that interference affects system performance. We actually classify systems as Wi-Fi or non-Wi-Fi interferers. In the case of non-Wi-Fi interferers, as shown in the slide, things like baby monitors, analog TV transmitters and microwave ovens can all play a role. The problem with non-Wi-Fi interference is it tends to be persistent, doesn't respond to the protocol. This means it can cause very severe damage to a Wi-Fi link. For Wi-Fi interference, we tend to find problems are more prevalent at 2.4 gigahertz because there's only 3 non-overlapping channels on channels 1, 6, and 11. The Wi-Fi system basically needs to sense the channel as quiet before it's able to transmit packets. So when there is interference present in the channel, this tends to result in reduced throughput as a result of your transmitter not actually being able to access the channel to transmit packets. The mobile client or tablet actually plays quite a strong role in the Wi-Fi performance. We actually find that client antennas are very directional. As you can see here in the picture, we're looking at the iPad antennas, and these devices basically radiate out through the Apple logo on the device, and they are very directional, almost like a torch beam. If you basically point the device towards the access point, you'll get a much stronger signal and a much better beta rate. Also, depending on how you orientate the device, you can change the polarization of the receiving antenna. It's important that the polarization at the receiver is matched to that at the transmitter. And again, this is an issue because access points are not all the same. Some transmit more vertically dominant polarization, some more horizontally dominant polarization. Certainly one of the pieces of work that we often do is to help access point manufacturers to get the polarization mixed and to try to create even illumination around a house so that performance is as insensitive as possible to the particular client. So this slide is interesting. It's actually based on some measurements taken by one of my colleagues in the University of Bristol. He actually took a scanning antenna into his house, basically rotated the receiving antenna in 360 degrees in order to generate images of the way the radio signals were impinging on the receiver. He then projected these back onto a simple database of his home. So in this particular slide here, you're looking at the link between the lounge downstairs and the bedroom upstairs. We can actually see from the central image that the power is actually bending and diffracting around the open door frame. It's actually quite surprising and interesting how deterministic radio signals propagate around your house. They actually do pass through the doors. They actually do pass up and down the staircases. Actually, many structures in your house play a significant role. For example, in this work, we found that large mirrors are actually very good passive reflectors. So I guess if you were clever, you could actually position mirrors strategically to improve the coverage in your house. As I mentioned, the antennas inside a Wi-Fi access point can play a very significant role, and it's often a major differentiator between products. We actually now work with quite a lot of Wi-Fi vendors in trying to help to get the antennas integrated as best as possible into their products. Often you find, in the past, that manufacturers have put the antennas in as an afterthought. They've often ended up forcing them into various places into the boxes that are not optimal. Sometimes the antennas are blocked by bits of the circuit boards, power supply, large items of metalwork. Very important also to note that antennas radiate very differently when they're inside the case with all the electronics than when you measure them on their own in situ. And so it's very important that you do analyse the antennas in the actual product. So how do we measure the antennas in access point? Well, at Bristol we use our anechoic chamber. As the video shows, this is a special room where we have cones on the walls, ceilings and floor to absorb the radio signals. Only the direct path comes out from the antenna under test. This is picked up in a reference antenna and then fed back to a vector network analyzer, which is possible to then determine the signal levels and the polarizations from that particular orientation. Again, the video shows the unit under test being spun around. We actually spin around in all azimuth and elevation planes in order to generate a full three-dimensional representation of the way that each of the antenna elements in the antenna product actually is operating. We can then combine these antennas in later software models to determine the exact performance of the Wi-Fi product. So here's one of the simplified outputs that we generate from the anechoic chamber. This is actually a 2.4 GHz system that had two antennas in it. So you can see each of the elements have got very different directional patterns. These axes are on a logarithmic, and basically the difference between the center of the sphere and the outer surface is about 40 dBs, or 10,000 times in power. So the little kind of lumps and bumps inside these plots are actually very significant, and in directions where there is a null, can significantly reduce performance and data rate of our system. What I think this diagram is very interesting at is it actually also shows the polarization. And it shows how the polarization varies with three-dimensional orientation. You can see the orange points on the pattern are vertically dominated polarization regions, and the blue are horizontally dominant polarization regions. Now this particular pattern is quite good, and you can see the blues and the oranges are nicely mixed around in orientation. However, not all antennas look like this, and sometimes it's possible to generate, as I mentioned, very vertically dominant or horizontally dominant antennas. And these can give very good performance in certain orientations, but in other locations they can lead to very poor performance. So when we don't really know what exactly kind of client is going to be used in the system, it's actually important to have this kind of good mix of polarization to get the best out of your access point. So now we've got our measured antenna patterns, we need to combine these with the multipath environment. Wi-Fi performance isn't just a function of the chipset or the products you use, but it's also influenced by the environment, in particular the scattering and how it's spaced spatially and temporally within your channel. What we see here in the animation on the right-hand side is one of our indoor ray tracing channel models. This is possible, or this software, it's possible to trace all of the multipaths, so we understand how the waves depart from the access point and arrive at your mobile device. We basically perform a process which is known as spatial and polarimetric convolution. And this process basically takes all these multipath components and combines them with the 3D patterns and polarization information from each of the elements. This allows us to build up an understanding of the channel structure between the access point and the mobile client. This information can then be used with a Wi-Fi system level model to determine the packet error rate and the throughput that we're expecting to see. Okay, we now basically take the channel data from the previous slide and use this with 802.11n or 802.11ac physical layer models. So at Bristol we developed standard compatible models, and these allow us to work out the throughput that we would see from an access point placed in any of the 10 rooms in this house to a client equally placed in any of these 10 rooms. Now we don't just look at a single link, we actually look at 1,000 links, so we place the client in 1,000 different positions in each room. And then take an average over here to get something more statistically relevant. We also spin the access point and the client full 360 degrees around the azimuth plane, because it's very important to look for this kind of angular sensitivity. I mentioned before that clients in particular are quite directive, and access points also can be, and it's important that they're designed to try to minimize this problem. So the table shows us a data rate between any client and any access point. To do this, we simulate all of the modulation encoding schemes, or link speeds, for each particular standard. And we choose the link speed with the highest throughput given a packet error constraint, which is normally no greater than 10%. And this table's excellent, gives us a really good understanding of the access point to client performance for a particular standard, bandwidth, antenna configuration, etc. But what's really nice about this is that we can bring it down to just a single number. In this table, 99.67 megabits per second. And we can compare the number from, for example, access point from vendor A with an access point from vendor B. And this is getting a lot of interest because it means we can actually say whether the access point from A is better than that from B. Okay, so we've talked a little bit about the Wi-Fi link, and now I want to talk a little bit more about media distribution. So media distribution over Wi-Fi is again a complex area. But as this slide says, is it possible to do high quality, reliable video distribution using Wi-Fi? And the short answer is yes, but it's difficult. You need to take a lot of care over the antenna designs in both the transmitter and the receiver. But the real secret is adaptation. Really important that you adapt the video encoded rate to the time varying wireless channel. As people walk around the house, basically the quality of the channel varies, the link speed varies. And it's important that we track this such that the video is always achieving its maximum quality given the opportunities that the channel is providing. So this particular slide is showing a wireless HDMI product from a company called Provision. Provision was a company that I co-founded in 2000, and this company is now selling these units such that you can basically take a HDMI signal from a set-top box, plug it into a transmitter, and then use the Wi-Fi standard to basically push that video content to any other room in your house. You simply plug a receiver into a TV via HDMI and you get the full look and feel, including remote controls and trick play, over the Wi-Fi standard. This particular unit uses 5 gigahertz Wi-Fi, and that's mainly due to the interference problems that we see at 2.4 gigahertz. Okay, so we've stripped it to home, but what about public spaces? What about outdoor hotspots? Is it possible to do media distribution in these places? Well, actually, within the actual session, there was an interesting discussion around the MBMS standard that is available, obviously, for 3G and 4G systems. One of the things that motivated us was that there was no multimedia standard for Wi-Fi, and yet it's obviously quite desirable to explore looking at whether we can do things like transmit TV channels out to clients over the Wi-Fi standard, or provide access to large data sets to very large groups of people. So basically, the UOB, in partnership with the BBC, Provision, Toshiba, Mubalu, and Archive, have developed a next-generation media solution that uses Wi-Fi broadcast, and it specifically looks at public spaces. So we've been looking at Slimbridge Wildlife Park and also Bristol Zoo as an area where maybe we can offer an interactive tour guide to customers that are basically looking around these areas. What we support is a number of live multi-stream videos, but more importantly also multi-gigabit data access into Android handsets and tablets. So it's a really media-rich experience, far more data than you would normally get in a standard app. And what's important is that all of the users are accessing obviously the same data set through the multicast system, but because it is multicast, we don't have problems with bandwidth or capacity. It's possible to support very large densities of users with this particular approach. So again, this project's very interesting, and we'll be doing a number of public demonstrations in Bristol Zoo in around August, September of 2014. So if you're around in Bristol in that period, come along and have a look at this technology for yourself. So looking to the latest devices, the latest and greatest Wi-Fi standard is currently 802.11ac, and this offers gigabit capabilities in the 5 gigahertz band. We achieve a peak rate of 1.3 gigabits by using 3 MIMO spatial streams, 256 quadrature amplitude modulation, a code rate of 5/6, 80 megahertz of bandwidth based on 234 active subcarriers, and a shortened guard interval of just 400 nanoseconds. Now, you're not going to see these data rates all the time. Clearly, as the bandwidth reduces from, say, 80 megs to 40 megs and 20 megs, you're going to see pro rata reductions. Also, the channel won't always be good enough to support, for example, 256 QAM. One thing that's nice about 11AC is it introduces something called anybeam technology. This allows beamforming, which is the focusing of energy from an access point to a specific client. This allows it to be used between any two devices, irrespective of the particular vendor of the chipset. In 11N, there were issues in that to get the best performance to your client, you needed to have the same chipset as your access point. AC is also backward compatible with 11N, so if you have 11N devices, they'll work very effectively. Also, we'll often run 11N on 2.4 gigahertz in a concurrent operation, meaning we can now support systems at 2.4 and 5 gigahertz at the same time. And again, given interference issues and congestion This is a good step forward. One thing it is worth mentioning on mobile devices is they usually just use a single antenna. So as a result, we can't run multiple spatial streams. This means we can't achieve the very high headline rates of 1.3 gigabits. They do this basically to save cost and reduce energy. But on top of that, normally the protocol stacks and the host processor loads seriously bottleneck and limit performance anyway. So we wouldn't normally expect to see more than maybe 30-40 megabit peak downloads on even an 11AC based mobile phone or tablet. Looking to the future, the next wave of 11AC, Wave 2, this is going to further enhance data rates by supporting 4 spatial streams. And more importantly, it will be possible with these devices to support 2 users at the same time in the same channel on the downlink. So basically, by turning on all of these tricks, it's possible for the sum aggregate data rate to rise to 6.9 gigabits per second, although this will be requiring the use of 160 megahertz of spectrum in the 5 gig band. So another interesting development in the Wi-Fi world, but one that's very relevant to the Mobile World Congress, is the recent IEEE high-efficiency wireless LAN activity. So whilst most people have been rather fixated on trying to improve the data rates in wireless LANs, actually quite often it's all about improving the user experience and the quality of the link as opposed to the headline rates. Now the high-efficiency group in particular have been looking at how we can combine wireless LAN technology as a complement to LTE-based mobile networks. And in fact, throughout Mobile World Congress here in 2014, there's an awful lot of companies talking about how they can do what's called Wi-Fi offloading. So how it's possible to ease congestion on the licensed cellular bands by using unlicensed Wi-Fi networks. So this is a big and growing area and one to watch out for as we move forward into the future. So moving to the end of this presentation, I want to end on, again, one of the very latest standards. It's known as IEEE 802.11ad, although a slightly more friendly term is YGig. So YGig is not technically part of the Wi-Fi standards, but is being looked at as a complementary technology. Unlike Wi-Fi, it operates in the millimeter wave bands. So this is up into the 59 to 64 gigahertz region. There's a huge amount of spectrum available up here, around 5 gigahertz. But more importantly, millimeter waves, the signals struggle to travel through walls and through floors and ceilings. And whilst this is a disadvantage in that it limits coverage to the same room and possibly the adjacent room, it actually allows you to run extremely dense networks. So one of the challenges as we go forward over the next 10 years is how we achieve densification with wireless technologies. How can we run access points that are being reused room to room, office to office? And the millimeter wave is a very interesting and attractive approach. But one of the problems of not being able to go through the walls is it also doesn't go through your body very well. And this is kind of a fun animation that one of my PhD students has put together. So we've been working on some computer models of the YGig physical layer. We've also implemented the YGig ray tracing models for indoor environments. And what we've done here is we've dropped down 4 or 5 people and we get them to walk around the room. Now what happens is one of those people's blocks the links between the access point and client. Because it's millimeter wave technology, the link is very adversely affected by the absorption of that body. So what the standard does is it uses, again, a form of codebook-based beamforming. So the idea is we basically manipulate a set of fixed phases across an array in order to push the beam in a different direction to try and get it to the receiver. So what you see in this animation is as users break the beam, we then search the codebook to find the next best set of beams. And you'll find that the signal effectively is then being bounced off a wall in order to get to the receiver. So one of the things that we're going to certainly see as we look at YGig and millimeter wave is much more emphasis on intelligent, smart and adaptive antenna arrays and beamforming systems. So one of the kind of killer apps that people talk about for AD is Click and Sync. So nowadays we're getting really large memory. I mean, an iPad can have 128 gigabytes of memory in it, and the speed to get the data off these devices was becoming a problem. Another great example is set-top boxes. If I'm leaving the home and I want to sync my content to my mobile phone because I never remember to do it, in good time, at the moment it takes a very long time, even over Wi-Fi. Whereas with millimeter waves, it's possible to get 6-7 gigabits per second, and in the future, I'm sure these will be even higher. So it's possible to transfer your movie data in the order of seconds as opposed to many minutes. Another good example is digital cameras. Again, very large memory cards. It can take a very long time to transfer the files, but YGig technology can do this in seconds. I think this could be one of the big consumer usage of this kind of technology. Okay, so that brings us to the end of the presentation. I hope you've enjoyed this content. We've talked a little bit about the Wi-Fi standards, how to make good access points, the sensitivity of clients to orientation. In terms of new standards, we've looked at AC and we talked about high efficiency wireless LAN activities. I also talked about YGig and the millimeter waves. For me, I think basically the trend towards merging Wi-Fi with cellular LTE is certainly one to watch. I think operators are pushing towards a single network with multiple heterogeneous wireless connections. The idea is to give us a seamless experience where, as a user, content just switches between the Wi-Fi and cellular technologies, always in order to give us the best access to the services we require. Anyway, if you've any questions, please do send me an email. As you can see here, andy.nix@bristol.ac.uk. And again, feel free to check out our website. And finally, thank you for watching this.